will today start our last module on system identification, and we will discuss some introductory concepts today before looking at the algorithms. It is important to in anything, before you really take a detailed look, it is good to take a bird's eye view or the big picture. So we will start from right from systems and models, modeling, what it involves, what are the factors that affect it, because system identification is basically about building models for systems from data. So if you do not know the model of a system, so far or in all our state estimation and filtering chapters that we have covered, or lectures that we have covered, we have almost always assumed except of course in cases like Wiener filtering, that the model is known, right? Now you have to somehow obtain the model. So in this last module we are going to look at how to obtain models of systems. So taking a rather, system is probably one of the most used and abused word in the, at least in the technical dictionary. It appears to me, I mean, it means 100 different things to 100 different people, and everybody uses it. So it is, I would not try to define a system because we all know what it is, but rather I would like to give some examples. I would like to start with some examples. For example, a VLSI circuit, or a circuit, VLSI or not, is a system. A chemical process could be a system. Our global weather is a system. Even the stock market is a system. So to be able to get an idea of what we mean by systems, to be able to arrive at an abstract definition, you must distill out the common features in these. What is the common feature? That there are, related to each one of them, there are some quantities of interest. For VLSI circuits it will be the voltages, and or for any circuit it may be voltages and currents, signals or their properties. For chemical processes it will be some chemical compositions, temperatures, pressures. We are interested in them for some reason, economic, social, technical, natural, environmental or otherwise. Similarly, if you have the weather, here also we are interested, we are very much interested in, there are some quantities of interest, and we would like to predict them, we would like to understand how they change. So it is also a system. So we always have some quantities of interest which we want to study or predict or control or whatever, and typically these quantities change with time, they evolve in time, right? And this evolution is, their evolutions depend on each other's evolution, so they are interrelated, and sometimes they are influenced by external quantities very often. Now what is internal and what is external? When we look at something for some purpose, we in general intuitively we fix what is known as a kind of, we imagine a boundary, right? This is the table, everything is, so all that is here are internal to the table system, while you are external to the table system. So in that sense, very fundamentally speaking, associated with every system there is a boundary, and whatever is, I mean, the things of interest within the boundary are supposed to be internal to the system, and I mean, you want to study that in great detail. That is your object of study. Everything else which influences it are external to it and are called its environment. So it turns out that this quantities of interest of the system which evolve in time are not only interrelated amongst themselves, they are also influenced by external quantities which are across the boundary. And this evolution in time is typically called the system's behavior. You know, related with systems, there are two terms which are used. One is called its structure, another is called its behavior. So anything, right? So structure, in a sense, why we use structure? Because we use structure because we can, you know, we always look for nice and efficient methods of dealing with complex systems. So we have quickly discovered that if you break it up and if you describe the overall system, complex system, in terms of small things, then it's useful. It's easier to understand. Using the same set of small models, you can build 100 different types of systems. So in a sense, it makes knowledge uniform. So basically a structured description of a system is where you try to describe a system in terms of smaller systems. So these smaller systems are typically called its components, right? So if you are interested in describing how a circuit is made of, let's say, smaller sub-circuits, then you are looking at its structure. While without looking at that, if you are generally interested in how things change in that circuit, then you are interested in its behavior, right? So in a sense, after all, how is that smaller circuit described? It may be described in terms of still smaller circuits. In this way, you will go down and down and down, and then finally you will come to a point where describing it in terms of smaller things is not useful. So at that point of time, you would like to directly describe it without saying that it is made up of smaller things. So finally, very simple objects only have behavior, they don't have structure. Their structure is actually trivial. But when you deal with complex objects, then you would like to compose new and new behavior using elementary behavior and then composing them. So you describe complex behavior in terms of simple behavior using structural concepts, right? I mean, that is the issue of structure and behavior of systems. So what I'm trying to say is that in a way, structure is also comes down to behavior, finally, eventually. So what are we interested in? We are interested in, because we want to understand behavior, we want to influence it, we want to predict it. So we want to, first of all, to be able to do anything like that, you need an unambiguous description for the structure. You need to, everybody needs to understand it in the same manner, and that's where, I mean, mathematics comes in. So you need to be able to understand such complex systems, you need to put it into a mathematical framework. So you need to describe the structure, or rather the behavior. So a model is nothing but a mathematical, can't write, the problems of being a minority, lefty. A model is a mathematical description that captures some desired aspects of system behavior under specific situations. So these are important things. So basically a model is a mathematical description of behavior, but it may not describe the behavior under all situations. So you may like to, because we in general, I mean the thumb rule in engineering is keep things small as it as you can, serving your purpose. So you may not be interested in constructing a grand mathematical model which describes the system under all situations. You may be concerned with very special kind of situations. So you build a simple model for that, and then you may not even be concerned with, for example, when we first learned circuits, in many cases we are not concerned with what is the, what is the power loss. So we simply model them as ideal elements. So if you are interested in power loss for some reason, you will model it. If you are not interested in power loss, you will not model it. So you only model those aspects which are of your interest, and you model them under the situations that you are likely to encounter in your goal. Not so in a sense, a model is a partial description of behavior. It is not a total description, right? So here what I tried to say, I have tried to describe that this is a system, it has a boundary, and it is influenced by quantities outside it. Such quantities are called inputs, and inputs may be either measurable or unmeasurable. That is, you may be aware of its existence, but in a given situation you may not be able to measure it. In another situation you may be able to measure it, but for the purpose for which you are building the model, in that situation you may not be able to measure some inputs. For example, if a machine is running, you may not be able to measure many things inside it. If you happen to stop it and really take it apart, you may be able to measure so many things. So it may be measurable or unmeasurable, and not only that, it may be controllable or uncontrollable, and it can happen in any combination. So it can be, in general, if it has to be controllable, in general it should be measurable. It is unlikely that something which is unmeasurable can be controlled, but something which is uncontrollable can be either measurable or unmeasurable. For example, disturbance in a system, it may be measurable or it may be unmeasurable, depends on whether you are willing to. Sometimes it's not just a question of physical measurability, it's a question of whether, it's not that whether really globally technology exists or whether it's possible to measure it. It's a question of whether the facility of measurement exists or not in that given situation. Due to some reason, you might have chosen not to measure it because maybe it involves more money. Whatever it is, but in a given situation, they may be measurable or unmeasurable, and controllable and uncontrollable. Similarly, typically we define two other quantities in relation to systems. The first one of them is the state. Actually, the state is nothing but the quantities of interest, things which you are interested in, things which affect the evolution of the quantities of interest in time. So such things are called state. They may be measurable or unmeasurable, and in general, depending on our purpose, some of the elements of these states or some direct functions of state we just choose to define as outputs. So generally, output, which one will be output, is a matter of definition. You can define this one as output and that one not as output, right? For example, you can say that in a motors, in a given situation, speed is the output. If you are trying to do speed control, suppose you are doing a machining application, then for a motor, speed may be output, because you say that is the prime thing that I am trying to control, that is what is my main object of interest. For the same motor, in another situation, position may be output, angular position. Suppose you are having an actuator, or you are precisely trying to position something, then speed is not so much important. Speed affects position, of course. Position is the integral of speed, but you may choose not to define speed as an output or directly even control it, right. So output is generally a matter of definition, it is generally measurable, while state may or may not be measurable. For example, in our last day's lecture, we acceleration, velocity, position all were states, acceleration and velocity were not measurable, while position was measurable by the sensor, right. Why we are saying all these is that all these, as we shall see, affects modeling of systems, and they will also affect model building. You have to remember it, though if you directly plunge into algorithms, many of these things will not be clear. So that's why in the first lecture it is good to stop and take a look at these things. So incidentally, so basically we are concerned with this constructing a mathematical behavioral description, and this mathematical behavioral description is affected by so many things. I mean, what kind of description you will choose? There are so many kinds of descriptions possible for the same object. It depends on many things. For example, it depends on the spatial scale of an object. That is, for example, suppose you are trying to model the temperature in this room. Are you interested to really capture the difference or variation in temperature in that corner from this corner? If you are interested, then you have to build one kind of model. On the other hand, if you assume that no, there are enough number of fans running in this room, so the temperature distribution is always uniform. So I don't need to really model what is this corner and that corner. That is not of interest to me. They will be slightly different, that is known, but how much different is not known to me. So I will take measurement at any point and then I just assume for my purpose that it is that the whole room is in that temperature. If you do that, then you will have to build a different model. So it very much depends on spatial scale, whether you are interested in modeling it. Similarly, it depends on temporal scale. For example, if we have clocked digital system, then we are not really interested, we are only interested in the state of the system at certain points of time. For example, in our discrete time model, we are only saying xk plus 1 is equal to axk plus buk. So this model describes the system behavior only at certain points of time, kt, k plus 1. What happens in between? We are not interested. Why we are not interested? Because we know that the interval is so small that it is definitely going to be somewhere between k and k plus 1, and k and k plus 1 itself are very close. So if I can find out xk and xk plus 1, in between it is going to be somewhere in between, and I don't need that kind of resolution. That's why you have chosen to use that model. That's why you have chosen to use that sampling time, and sampling time is an integral part of the model because it appears in the parameters. For any system, the sampling time appears in the discrete time model parameters. You must have seen it in when you tried to construct Z transforms with sampling time. So the model you choose depends on the temporal scale at which you want to examine phenomena, very much. Similarly, it depends on the numerical scale at which you want to. You see, the temporal scale is actually the x-axis. If you are generally interested in, you are generally interested in evolution of a thing in some dimensions. So here I have covered 3 dimensions. Here I am covering the 4th dimension, time. And then finally you have to also see what is the value of the variable over these dimensions. So there also you may be interested in various scales. For example, do you think that a logic gate really does not exist at any other voltage value other than 0 and 5 volt? It does. It very much does. How can it suddenly transform itself from 0 volt to 5 volt? when it goes from 0 to 5, it actually goes through all the voltage values. But when we deal with logic gates, we don't at all bother about that. We treat them as zeros and ones. Why? Because of the fact that that in its overall life cycle, the amount of time in which the logic gate lives at a voltage, let us say between 0.4 and 3.2, between that band is infinitesimal. It either always is below 0.4 or 0.6 or 0.2, whatever, and it's always above 3.2, 3.4. So 99% of its lifetime it remains in those two voltages. So that's why you have chosen to ignore that other 1%, and you have decided, so you have adjusted your numerical scale of values. You have the whole scale from 0 to 5, which could be modeled by a real number, you have chosen to describe by two integers, 0 and 1, right? And that, as you can see, completely changes the model of the logic gate, right? So it depends on numerical scale. It also depends on various properties of the inputs that you want to consider. For example, we will typically build DC models. See, for a transistor, we build either a high frequency model or a low frequency model, which are quite different. Why? Because in one case we assume that it will take high frequency signals input, in another case we assume that it will take only low frequency signal inputs. So we characterize so the model is selected based on the input characterization, correct? Similarly, there can be various kinds of model forms. I mean, we may constrain our model selection just by various conveniences. For example, we always look for linear models. Why? Things are not linear, but we sort of force them into, even if they are non-linear, we would find all kinds of excuses to do a linear modeling. Why? Because for further purposes, since we know the linear theory, that you can construct a grand nonlinear model with which you can do nothing, or you can construct an approximate linear model with which at least you can progress. Maybe you can design a controller. So that's why, because looking at the future usability of the model, you would like to a priori constrain that no, I am only going to build a linear model, whatever it takes. I am not interested in building nonlinear models, even if the system is nonlinear, or even if it could be described better by nonlinear models. So we might like to, for various purposes, we might like to constrain the model form, right? Similarly, there may be several other factors. There may be measurement constraints that immediately decides between which and which variable it is useful to build the model. If you want to use the model, you must generally build it between two measurable quantities. Similarly, you may have knowledge constraints, or you may have knowledge advantages. For example, you may already know that a system is stable. So if you happen to know it to be stable, I am calling it a knowledge constraint, because constraint means in mathematical terms it means that it will define a smaller space than the overall space. So if you already know that the system is stable, then you will only look for stable models. You will not look for unstable models. So you will have to devise an algorithm which will automatically reject unstable models, because you already happen to know that it is stable. I mean, it is not a constraint in the sense that it is a disadvantage. It is actually an advantage. So you will have to, sometimes we call it a priori knowledge. That is, before we start looking for a model, what do we know? What is our experience? We should be able to use it. Then there may be computing constraints. For example, in a given situation, if you ask an aerospace engineer, he will say, no, don't give me complex, particle filtering algorithms. recently, I mean, this in I mean, signal estimation, that is an approach which is receiving a lot of attention. It is said that it can produce better estimates than usual Kalman filtering and things like that. So people are now doing a lot of research on that. But if you ask a practicing aerospace engineer, he will say, no. What is this a particle filtering? It may be very grand, but my onboard computer cannot perform this every cycle, every guidance cycle. I cannot accept it. So you must use a Kalman filter. You must use the corresponding models. So here it is the computing constraints which restrict you to choose a model, right? So there could be various kinds of application requirements also. So what I wanted to say is that the model of a system is not absolute. It is actually a decision. It is actually it's like you will have to look for a model. But while looking for a model, just like you shop for a thing in a market, similar to that. But while you do that, there are various other considerations which will guide you, which may be related to your situation or which may be related to your purpose, either of them. All of them are either related to the situation given to you about which you cannot do anything, and or it will be related to the purpose that you want to put the model to, right? So that's what I wanted to say, that so many things will finally determine what kind of model you have to look for, and then satisfying these things you have to look for a good model. Probably you will have to look for the best model in some sense. So that is how to do that is system identification. So first of all, naturally you can see that we are, I am talking in very general terms, rather general terms, but so we'll have to define before we actually describe algorithms that what do we decide for these things. Am I looking for a symbolic model, or we'll have to define our scope in which we are going to study, because model building is a very, very vast subject. So in this small set of 6 or 7 lectures, we are going to cover only a small part of it. So we will say which part we are going to cover in our lecture. Before going on to that, there is another concept. This is something which I really like to explain. That is, the same quantity, the same thing, the same physical thing, you may choose to model it in 5 different ways. In fact, people, for the same thing, there are different sets of people who actually model it in 5 different ways for their own purposes. So for example, this is my pet example, that you take a digital VLSI circuit. Suppose you take a signal processor chip from TI. It is a device. What is it made of? So in this case, it will not be von Neumann model. It will probably be a Harvard architecture. So when you look at the signal processor, it contains millions of transistors. So obviously you first say that it is a device, it is a system. How does it work? What is its model? So you say that it is for general purpose computers like a PC, you will say that it has a von Neumann model. Somebody say that it has a Harvard architecture. Signal processors typically do not have Harvard architecture. So what do you mean that this chip has Harvard architecture? You are obviously trying to describe its behavior and its working at some level using some predefined concepts. So the Harvard architecture has been defined using other concepts. So you are looking at it as a device of Harvard architecture. What is the Harvard architecture? Somebody asks. So then you can, maybe this step may be too abrupt. I mean, you may be defining a Harvard architecture in terms of lower level devices. ALUs. I'm not very familiar with the Harvard architecture. So you may come down to small computing units which are computed in a particular way. That is called the Harvard architecture. Well, how are they made? So if you ask, somebody will say that it is, how does it function? What is its behavior? Each modules. For example, one of the important components in a signal processor is the multiplier. That's why signal processors are so fast, because they have a hardware multiplier. So how does the multiplier function? What is its behavior? So you say that it is a state machine. It has certain lines. It is a sequential circuit, typically described as a finite state machine. So at that level, you think it's a finite state machine. What is a finite state machine? Oh, it is a model for any circuit which is made of logic gates. So now you have come to logic gates. What is a logic gate made of? It's made of transistors. What is the transistor made of? You know, remember, I read a story where an ancient lady scholar called Gargi. It was not a lady scholar. It was a sage called Yajnavalkya, who kept asking. Gargi actually kept asking Yajnavalkya about what is this made of, what is that made of, what is that made of, and then finally, I mean, it was becoming very abstract and it was becoming very deep. So you see, from a digital VLSI circuit, we are from transistors. If you say what makes transistors, you will have to say electrons and holes. Then if you say what makes electrons and holes, then you go to subatomic physics, about which I know nothing. It is the same object. Now why should you now tell me that now you will find that everybody is interested in this model. Somebody is interested in each level. For example, the person who is designing the process for making that, the actually semiconductor manufacturing process, he all the time looks at it like this. On the other hand, suppose when you design a digital circuit, you don't bother whether it's made of transistors, do you? You are only bothered with its truth table. But the person who has designed the gate, he had to really bother about what are the transition time, how fast does it rise. So he had to really look at the same gate as a nonlinear transistor circuit for his purpose. So the gate designer who has designed the gate which you use, he never looked at the gate as a truth table. He looked at it as a nonlinear differential equation coupled, representing that transistor circuit. On the other hand, you always look at it as logic gates. Somebody who wants to design software for your signal processor, maybe internal software, he doesn't even bother about logic gates. He is only bothered about its abstract behavior. So he looks at it as a state machine. And finally, the computer architect may not be even interested in it as a state machine, because it will have millions of states. He may be interested in higher level models, and it is the same digital VLSI circuit. So that's what I wanted to say, that the same physical entity can be modeled as multiple model abstractions, and you may need to do, it's not that you need to always model it at one abstraction. It totally depends on your purpose. And so you must decide that at what abstraction level you want to model a system. That will, give you answer to all these questions, and then focus your search for models, right? So having said all that, let's focus what are we going to look at? So this is just a kind of a taxonomy of models. Just describes this is incomplete. You could have various other cases or categorizations. So here I have defined models as, this is offhand, symbolic. You may have, for example, a digital circuit. You are calling as made of zeros and ones. Those zeros and ones are not numbers. They are not to be treated as integers. They are actually nothing but symbols. Okay. So the digital circuit is symbolic model. On the other hand, you may have numeric models, and we are interested in the numeric models. Now, numeric models could be either static, where the value at a given point of time depends on other values, but at the same time there is no extension of time towards the past, or it could be dynamic. We are interested in the dynamic model. It could be spatiotemporal, that is in how many dimensions you are talking about. Actually, I mean, arbitrarily speaking, that's why I wrote it here. There could be, it's not necessary that I mean, everything has to take place in 4 dimensions. It can take place in n dimensions in general, because all systems are not physical, right? So for example, that is precisely why I gave the example of the stock market. It is not a physical system. So but we are generally concerned with physical objects. So it could be either spatiotemporal, where you are interested in studying the variation with time and with space, or it could be only temporal. We are interested in only temporal. A temporal dynamics can be either linear or non-linear. For most purposes, we will be concerned with linear because of simplicity. A linear system could be finite dimensional or infinite dimensional. For example, e to the power st is an infinite dimensional linear system. So we are generally interested in finite dimensional system. If you construct a state space description of it, it will have a finite number of states. So we are interested in finite dimensional systems. Finite dimensional linear systems could be treated either in time domain or in transform domain. Sorry, we are not going to take it in transform domain. We are mostly going to take it in time domain, because basically because of the fact that then you can directly use signal values. You could go further down. For example, a linear finite dimensional time domain model could be either time varying parameter or time invariant. It could be either single input or it could be multiple input. There are so many other categorizations, but suffice it to say here that we are generally interested in linear finite dimensional, actually single input single output, and actually, though it could be varying, but generally interested in time invariant models. So we will treat that the model parameter is generally that the system model parameter is constant but unknown. So we have to find it, but it does not change all the time. So that defines the, you see. So after telling such a big story, I have come down now finally to the right. So this is what we are going to consider in this lecture. Now in such models, now we are gradually settling down to business. We want to identify, we want to find out a good model. So what is the model made of? What are all the things that we have to find out? So model is typically made of structure, parameter, and signal values. These are the 3 entities which make a model. So what is the structure? It is a particular mathematical form. For example, if you have xk plus 1 is equal to axk plus buk, this mathematical form that this is a vector, that this is a n by n matrix, this particular mathematical form is called its structure. That's how things affect one another, right? Then you have, so basically when you tell a structure, you are defining a class of models. So this is a class of linear finite dimensional time invariant systems. You are not talking about a particular model of this circuit. You are not saying that. You are talking about a set of models, all of which can be described by that structure, right? And now you are in general interested in building a model for something. So once you have defined a set, that set serves like a bag. Now in that bag there are so many bags of models. So in how many bags will you search? So you have defined that no, I am going to search from the systems in this bag. So when you have defined the model form, you have defined that. Now in that bag you have to pick out a particular model. So how is that bag characterized? In terms of the parameter values. This is a matrix. What are the exact element values in that matrix? They are called parameters. So a model set which is characterized by the mathematical form or the structure is instantiated by the parameters. If you put the parameter values, you get a particular model of that structure. And then finally, to complete the model, after all, it's a relation of signal values, so you have to have the signal values. So you have to have xk and uk. That gives a model, right? Now generally we say sometimes, so all models will, as I have described, all models are called parameters. I mean, all models have parameters. That is a fact. But still some models are sometimes called non-parametric models and some models are called parametric models. Why? Because generally we have always finite descriptions are good. Remember that we wanted to have algorithms where as time k goes up, if you have to describe all, if you have to compute all signals from 0 to k, then you are in trouble because k goes on increasing. So every time your work increases, your memory increases. So in general we are interested in those model forms which have a nice finite set of parameters by which you can characterize the model. On the other hand, there are some systems, some model forms, some mathematical forms in which there are still parameters, but those parameters are very large in number, and I mean so they are not really called parameters. So such models are called non-parametric models. For example, the same system is either described like this or described in terms of its impulse response. Now the impulse response obviously is could very well be of infinite duration. I mean, it does not come to 0. So in which case this model, the same model, here also yk, here also yk, with the same uk's. This is described by an infinite set of parameters as k goes on, while this is always described by the elements of A, elements of B and elements of C, which are always finite. So that's why this kind of models are called parametric models, while this kind of models are called non-parametric models, because here the parameter set is too large, to be conveniently used as parameters. So we will be generally interested in parametric models. Now in many cases we will assume, for most of the lecture we will assume that the model structure is kind of known. At the end we'll spend one lecture to see how we can even choose model structure, but generally we will mostly assume some model structure and then find out that given that model structure, how to pick out a good model. So how do you determine model structure? If you are given a circuit, if you are given a circuit diagram, say of RLC circuits, how will you know whether it should be of second order or third order? Are you going to do it by trial and error? No. You are going to look at the circuit, you are going to write the equations, as many energy storing devices, as many states. So if it has 2 inductors, if it has 2 capacitors, you will immediately know that it will have 4 states, even before writing the equation. And probably the exact model structure, you will write basically the KVL KCL equations, and from there you will get the model structure. Such a model structure you have determined physically, that is from physics. Again, that means you have implied its structure. You have got the sort of deduced the model of the composed system in terms of models of inductors and capacitors which you have learnt in college, right? On the other hand, the same RLC circuit, if it is given in a box to you and said that these are 2 terminals, these are 2 terminals, it is a linear system. Please find the model structure. Then you don't know what's inside, you don't know the circuit, so you can't do it physically. Then you have to do it numerically, and there are methods of doing it. So a model structure may be determined either physically, or physically means based on physics based arguments, based on the device physics or the system physics, or numerically. And we must remember again and again, I am telling that it is valid under specific conditions. For example, when we are doing a linear modeling, it is in many cases valid under small signal conditions, where there is an operating condition which the circuit people call a bias. If you are a transistor amplifier designer, you will call it a DC bias, on which you have small signal variations. On the other hand, the chemical engineer will call it a operating point, around which he has signals vary. So in any case, signal must be small for that model to be valid. So this is the case. For example, if you have chosen to choose an ordinary differential equation model, it means that you are ignoring spatial distribution. Otherwise, you would have gone for a partial differential equation model. Similarly, low frequency, low amplitude model. Low amplitude is here, even low frequency and high frequency models as we described, or models. Sometimes you will have to construct, also utilize models for disturbances, even sometimes for unmeasurable disturbances, right? For example, you have already done that in your Kalman filter. You have used a disturbance which is unmeasurable in your model. So you have, so I mean, how do you know that the disturbance acts like that? So it will act, it will be that only if there are certain mathematical conditions. For example, only when the power spectrum of the disturbance can be spectrally factorized. So, and there may be several kinds of technology constraints. Some things may be measurable, some things may not be measurable. So the model structure will inherently depend, can be determined, but we must, after we make an assumption on that, we are not going to look back. Then we are going to look for our system in that bag. But we must remember that that bag selection is done somehow and is valid under certain conditions. So if those conditions are invalidated, those parameters will not work anymore. Now, even in that bag, now we are gradually coming to how to choose. Even in that bag, there may be big models and there may be small models. For example, if you specify, it depends. You know, it's always like a Russian doll. So there will be a bag inside a bag inside a bag, right? So first you define a big bag called linear finite dimensional model. Then you say linear finite dimensional models of order n, right? So then you may like to say, okay, linear finite. I'm going to look at it in the bag of linear finite dimensional models. But then of what order? So which bag in that bag? So we must. So it is important to be able to decide the appropriate model complexity. After all, we want to keep things the simplest for our purpose. So we will choose the simplest model based on two considerations. First consideration is that it should be able to approximate the system in that situation reasonably accurately, right? And another thing is that since we are looking for, sometimes we say that since we are looking for a model in an automated manner, you know, it helps us to find a situation where we will always converge on one model. If it turns out that there are 5 different models, any one of them could be picked up, then it so happens that my algorithm, especially if I am looking at the model online, then my algorithm may just wander. Sometimes from here and there it will shift. Such things may happen. So uniqueness is important. Now, what I wanted to say is that, so I'll make some comments about this approximation and uniqueness. First thing is that we must remember, this is a thumb rule based on which the whole field of robust control is based, is that system complexity is always greater than model complexity. So the model is but an approximation of system. There is always some unmodeled dynamics, always. I mean, almost always. Similarly, model complexity varies. I mean, it is a matter of choice. For example, this e to the power minus st, you may model either as 1 by 1 plus st, or as 1 minus st, or as 1 minus st by 2 by 1 plus st by 2. Within certain frequency ranges, these are all valid approximations of e to the power minus st. Which one you will choose depends. Similarly, now, so you have to choose the, now you cannot choose two complex models because they will lead to loss of uniqueness. For example, if the system data is really generated from a system like this, which has a transfer function, okay, k by s plus a, then remember that if we are looking for second order models, then we will get we'll get so many choices, because this second or all such second order models for any value of b will actually fit this system. So the solution is highly non-unique. There are infinite number of second order systems which will fit this first order system. Why does it happen? Because you have unnecessarily considered a model which is too complex. It was not necessary. On the other hand, if you choose an oversimple model structure, then you will not be able to approximate. For example, if the system Bode plot, if you model a system by a first order Bode plot, then you will never be able to model. You will be able to model up to this maybe, but if the system has another pole here, then you will never be able to model this thing. If you always choose a first order model. So if your depends on your input spectrum. If your input spectrum only stretches up to this, it's fine. If it stretches up to this, you will never be able to fit a first order model. There you have chosen an oversimple model structure. So I'll stop you just by defining what is system identification. So basically, given a set of process signal values over time, given an assumed model structure which could be based on so many considerations that we described today. So now we have defined the bag. Now in that bag we have to pick a good model. So what do we mean by good? So we have to define some measure of goodness, which is an approximation error criterion, and you may also actually this is also, you know, actually these two together define the bag. So you may also say, you may not only say linear finite dimensional, you may also say linear finite dimensional stable. So when you are saying stable, you are further dividing the bag, and obviously now if you want to find out the poles and zeros of the system, you are going to look in the left half plane. So you are using a priori knowledge to first get to the smallest bag, and then in that bag you will have to pick out the best model according to this approximation error criterion. This is the problem of system identification. So determine a model that results in the least approximation error according to the stated criterion and satisfies the model constraints. That is the problem which we are going to handle from tomorrow. Thank you very much.